All right, my good friends, good to have you back. This is Unit 16, Reaction Kinetics. This is the fifth installment. Remember that if you're following in the Zoomdoll book, we're still on 12.4. We've got zero order kinetics under our belts now, and now what we need to do is finish up with first order rate law, and hopefully also in this video, second order rate law. We'll see how we do on time. So here we go. First order rate law. Let's take a look at this equation here. We've got N2O5, that's 2 moles of that, converted to 4 moles of NO2 plus O2 gas, right? Now let's just say that we take a look at the data and we determine that when we double the N2O5, the reaction rate, guess what? Doubles. So if you double reaction rate, when you double the concentration of the reactant, you're dealing with first order kinetics rather. First order kinetics, so you should know that. So let's start by writing the differential rate law. We're good at that now. The differential rate law for this reaction. So we'll start with rate is equal to minus the change in the N2O5 divided by the change in time, right? Okay, that's how fast N2O5 is disappearing in this first order reaction. But now let's write the differential rate law. That's equal to K, some value of K, some rate constant, times N2O5 to the first power, right? That's it. That's the rate law, the differential rate law anyway, for this first order kinetics reaction. But what we want to do now is we want to look at this and take a look at what we call the integrated rate law, all right? Now, technically, you would need to know calculus. In fact, you need to know a procedure called integration in order to get or obtain the integrated rate law. As it turns out, it's not important that you know how to calculate it. You just need to know the bottom line. And this is it. This is the star of the show right here. This is the integrated rate law for a first order reaction. You just got to memorize it. Here we go. It's the natural log, and yes, that is natural log base E, not base 10, not log, but ln. So the natural log of the reactant, which is N2O5, is equal to minus Kt, that's minus Kt, plus the natural log of the concentration, the initial concentration of the reactant, that's N2O5 naught, right? So that's it. That's the integrated rate law, all right? If we take the natural log of the concentrations and we plot that against time, we should get a straight line, right? We should get a straight line. Now, the straight line is going to have a negative slope, but that's not going to bother us. So let's take a look at what that's going to look like graphically. Again, if you have first order kinetics, remember for zero order kinetics, concentration versus time was a straight line. Had a negative slope. That wasn't a problem for us. But it was concentration versus time that gave us a straight line. This time it does not give us a straight line. Notice also if we look at the reciprocal of concentration versus time, no straight line. But look what happens when we plot the natural log of concentration versus time. By the way, all these should have time, all these should have time as the x-axis, right? But again, log of concentration versus time yields a straight line. Negative slope, but that's not a problem. We just say K is equal to the negative slope. So we calculate the slope, rise over run, and the negative of that number will give us the K value for that first order reaction. All right? All right. Let's move on. Before we go to second order reactions, one order of business, no pun intended, one item that needs to be corrected, or not corrected, but addressed, and that is the half-life of first order reactions. Now, I do want to make it clear that you are not responsible for the derivations of any of these half-life laws. But I thought there might be somebody out there who might be interested in the derivation, so thought I'd go ahead and do this one for you. All right, so here we go. Once again, though, let's review. T1/2 is the half-life. It is the time required for half of the reactant to turn into product. So how do we get to the half-life reaction? Here's what we do. We start with the integrated rate law. Natural log of concentration, natural log of A, is equal to minus KT plus the natural log of A sub 0. That was the integrated rate law that we looked at just a minute ago. So what we're going to do now is we're going to make some substitutions. In fact, we're going to make a couple. What we're going to do is we're going to say that at the half-life, at T1 half, that the concentration that's present, in other words, A with brackets around it, is equal to the initial concentration divided by 2. That's what half-life means. That's the definition of half-life. So we can make that substitution. You with me? So here we go. We're going to say that instead of writing natural log of concentration of A, we're going to say natural log of concentration of A naught over 2. There's the substitution right there. Is equal to minus K, but we're interested in a specific time. Not any old time, but the half-life, right? So we're going to say that's equal to minus K T1 half plus the natural log of concentration of A initial, all right? Now what we're going to do is we're going to do a little bit of mathematical manipulation. We're going to have the natural log of A sub naught divided by A sub naught divided by 2. See how that happens? All right. We have a log here. We have a natural log here, natural log here, natural log here. So we're going to bring one to one side. When you subtract, you divide. So that is equal to K times half-life. Therefore, here's what we're going to do. We're going to cancel, let me put this in a different color because it's kind of hard to see. We're going to cancel this with this, and we're going, remember there's a 2 on the bottom here, so we're going to rewrite that as the natural log, that 2 comes up, the natural log of 2 is equal to K times half-life, or T1 half. Now let's rearrange that. We've got T1 half is equal to 0.693, which is, by the way, is the natural logarithm of 2. Check it on your calculator if you don't believe me. So T1 half is equal to 0.693 divided by K. Now all of that is just brain food. What you need to remember is the half-life reaction for a first order reaction. That's it right there. T1 half is equal to the log of 2, which is 0.693, divided by K. Notice that the half-life reaction for a first order reaction does not depend on the initial concentration. That's important. It does not depend on the initial concentration. It's kind of like radioactivity. If I told you that polonium has a half-life of 2,174 years, it doesn't matter how much you start with, that's the half-life. So radioactivity, by the way, has first order kinetics. It doesn't matter how much you have to begin with. It's only a question of, well, the question is, what is the half-life? So in this case, the half-life for a first order reaction, once again, 0.693 divided by K, and we're done. All right, let's take a look at second order rate laws. This won't take too long. It says, for the general reaction involving a single reactant, the rate law is rate is equal to, let's write rate is equal to minus the change in concentration of A, that's the reactant, over time. So if we write the rate law, I'm talking about the differential rate law, that's equal to K times concentration of A to the second power this time. It's a second order rate law, so it's to the second power. So the integrated second rate law has this form. Okay, the integrated rate law for the second order reaction has this form. Notice this time we're going to take the reciprocal, right? The reciprocal of the concentrations. So here it is. This right here, ladies and gentlemen, is the integrated second order rate law, general rate law. We have 1 over a concentration, right? 1 over A is equal to, let me just put some concentration brackets around that A. So we have 1 over concentration of A is equal to K times T plus 1 over concentration initial of A. You may ask, didn't you forget to write a negative sign in front of that K? And the answer is no. I did not forget. This is the only rate law, the second rate law, second order rate law between 0, 1, and 2 is the only one where K is not the negative reciprocal, or excuse me, the negative of the slope. It's simply the slope. What does that look like graphically? Let's take a look. Here we go. So, from a graphical point of view, if we look at concentration versus time for a second order reaction, we do not get a straight line. If we look at the natural log of concentration of A versus time, again, no straight line. However, if we look at 1 over the reciprocal of the concentration versus the time, we get a straight line and it has a positive slope. So we don't have to take the negative of it, right? It's just K is equal to the slope, all right? Hope that makes sense. Now, let's talk a little bit about the half-life. The half-life expression for the second order reaction, and I'm not even going to bother you with the derivation. It is this. It's T1/2 is equal to 1 over K times A sub naught. Notice once again that the only half-life expression that does not include this initial concentration term is that for a first order reaction, right? That is for a first order reaction. Not second order, not zero order, first order only does not involve the initial concentration. All right? Okay, folks, I'm going to leave you with a little bit of a mnemonic because I know you've got a lot to remember. This helps me to remember. I'm not sure. I hope it'll help you. But here we go. Folks, when I was a little boy, there was a cleaning material called CLR. I have no idea if it still exists, all right? But it was called CLR. And people used it to clean drains and things like that. And I use this as a mnemonic, all right? I use this as a mnemonic. If you plot concentration versus time and you get a straight line, that's a zero order reaction. If you plot the natural logarithm of concentration versus time and you get a straight line, that is a first order reaction. And finally, if you plot the reciprocal of the concentration versus time and you get a straight line, we're talking about a second order reaction. Folks, CLR 012. I hope this helps. You have a good afternoon or evening or whatever time you're listening to this, and we will see you on the next one. Thanks. Bye-bye.